Welcome to the Deep Dive, where we take your stack of sources, research papers, and articles and distill them into the crucial knowledge you need to be quickly and thoroughly informed.
Today, we're focusing on a climate solution that sounds a bit like science fiction, but it's really just, well, it's geology in fast forward. We're talking about enhanced rock weathering, or ERW.
I love this idea. It's an engineered negative emission technology that essentially takes one of Earth's oldest, slowest climate mechanisms, the natural weathering of rocks, and just steps on the accelerator.
Exact.
We're turning millions of years into decades.
That's it. If you've ever wondered how the planet naturally draws down CO2 over these vast geological periods, this is it. Silicate rocks erode very slowly and lock up carbon. ERW just speeds that all up by grinding the rocks into a superfine powder.
And the mission for this deep dive is clear. We've synthesized everything from peer-reviewed literature to the latest field trials, and we really need to answer two huge questions for you. First, can this tech realistically hit that gigaton scale?
The scale needed to actually fight climate change.
Right. And second, what are the logistical, energy, and environmental costs that might just stop it dead in its tracks?
It's the ultimate promise versus practicality challenge. So if you take away just one piece of knowledge right now, it's this. ERW involves applying crushed, very specific silicate rocks.
Things like basalt or olivine?
Basalt, olivine, or wollastonite. Yeah. You spread them on soils, mostly agricultural land, all with the explicit goal of capturing carbon dioxide.
Okay, let's zoom in on that core mechanism. We really need to get the chemistry, because that's where the incredible durability of ERW comes from. So when we spread this mineral dust on a field, what's the very first thing that happens to capture atmospheric CO2?
It all starts with water and air. When atmospheric CO2 dissolves in soil water, it forms carbonic acid. It's a weak acid, the same stuff that gives soda water its fizz.
Okay.
But it's the key driver of this whole process.
So you have this slightly acidic water, and it's percolating through the rock dust we've spread out, which I assume maximizes the surface area for the reaction.
Exactly. And this weak acid, it attacks the silicate minerals.
Wow.
Let's just say the crushed rock is wollastonite. When that acid reacts with the mineral, the key is that it consumes the CO2 molecule.
It consumes it.
Yeah, and it converts it into a dissolved, stable salt.
So you're not just trapping the CO2, you're chemically changing it. What's the end product?
The primary product is bicarbonate. It's essentially a dissolved form of inorganic carbon. What's so fascinating is that we've taken a gas CO2 and turned it into a dissolved ion in the water.
And that conversion is the secret to the durability. Where does this bicarbonate go, and why does that make it so long-lasting?
It follows two extremely durable pathways. The first, and probably the most robust for climate mitigation, is what we call ocean alkalinity enhancement.
Okay.
That bicarbonate is carried away by soil water, then into rivers, and it eventually just flows right into the ocean.
And once it hits the ocean, let me talking, for storage.
This is the real selling point. This carbon, now stored as increased ocean alkalinity, it stays there for massive timescales. The estimates range from 10,000 up to 100,000 years.
Wow.
Yeah. That is permanence measured on a geological clock.
That's incredible. It's one thing to trap carbon in a tree for, a century. It's another thing entirely to lock it away for millennia. You mentioned two pathways. What's the second one?
That's pedogenic carbonate formation. As the rock weathers, it releases calcium ions. And these ions can react right there in the soil with the bicarbonate to form stable calcium carbonate.
So basically limestone.
Essentially, yeah. Which keeps the carbon sequestered right there in the soil profile. Still very durable.
Now, we absolutely have to clear this up. I think it's a common point of confusion. Farmers have been spreading powdered rock for ages in the form of agricultural lime, which is just calcium carbonate.
Right.
How is ERW fundamentally different from that?
It's a critical distinction, and it's all about what you're starting with. Traditional liming using calcium carbonate is generally considered carbon neutral. In some cases, it can even be a CO2 source because dissolving the limestone can release previously stored CO2.
So liming isn't adding a net sink for new atmospheric carbon.
Exactly. But ERW, because it uses silicate minerals reacting with atmospheric CO2 through that carbonic acid we talked about, it provides a true permanent net CO2 removal from the atmosphere. You're turning a rock into a carbon sponge. Now let's pivot away from the pure chemistry for a second and talk about something really surprising that came out of the field trials, this double benefit.
Okay.
Initially, when scientists modeled ERW, they were just focused on that inorganic carbon sink. But the impact on the living soil, on the whole ecosystem, is proving to be just as substantial.
This is where ERW steps out of lab and into the farm. It doesn't just draw down carbon, it acts as a kind of natural fertilizer. So how does that boost the soil's ability to store carbon organically?
It's all about the nutritional inputs. As those silicate minerals weather, they release essential micronutrients for plants: calcium, magnesium, potassium, phosphorus, silicon.
It's a natural, slow-release fertilizer.
Precisely. And better fertilizer means bigger, healthier plants, right? More photosynthesis, deeper roots, and higher inputs of carbon back into the soil.
And the data on this is good.
The data is compelling. Field trials have shown crop yield increases from 9 to 21% overall. And to put a specific number on it, in the U.S. Corn Belt, they saw maize and soybean yields jump by 12 to 16%.
A 16% yield boost is huge. That's a serious economic incentive for a farmer on top of any carbon payment.
Absolutely. But the benefits go beyond just bigger plants. The sources suggest ERW literally changes the soil structure to stabilize the carbon that's already there.
How does that work?
Well, when those basications, especially calcium, get released, they increase the soil pH, they reduce acidity. We see soil pH moving, for example, from, say, 6.47 up to 6.76. It seems small, but that shift is huge for soil chemistry.
And what did that do for carbon storage?
It enhances the formation of something called mineral-associated organic carbon, or MAOC. You can think of MAOC as the carbon that's physically stuck to soil minerals, so it's protected. Vacations act like bridges, chemically linking organic matter to mineral surfaces. This physically shields the existing organic carbon from being, broken down by microbes.
So you've got this protected long-term stuff, the MAOC, and then the looser stuff, which is particulate organic carbon. Do we have a sense of where the gains are?
We do. A global meta-analysis of 74 experiments confirmed this. Total soil organic carbon went up by 3.8% on average, but the protected fraction, the MAOC, increased by 6.1%.
So it's building the most durable kind of soil carbon.
Right. Even the looser particulate organic carbon saw a 7.5% increase. The key takeaway for you is that ERW isn't just capturing new carbon, it's helping the soil hold on to the carbon it already has.
And if that wasn't enough, there's a really important non-CO2 co-benefit that makes ERW shine in farming.
This is a major bonus. ERW can actively mitigate nitrous oxide, N2O. That's a greenhouse gas nearly 300 times more potent than CO2.
Wow.
Yeah, and research using basalt found it reduced cumulative N2O emissions by 29 to 32% in some maize systems. It's because that pH change redirects the nitrogen cycling in the soil. It's tackling 3 problems at once: CO2, soil health, and N2O.
Okay, the potential is massive. The co-benefits are clear. Now for the big question. Can this actually scale globally? Because if you can't hit the gigaton scale, it's just an interesting science project, not a real solution.
The models, they're optimistic. Integrated modeling suggests that if we deploy ERW across all global croplands, the potential is between 0.5 and 2.0 gigatons of CO2 per year by 2050.
That range puts it firmly in the category of things we have to pursue for net zero.
Absolutely, it's a serious contender.
That's huge, and I know that number is just for cropland.
Oh.
What happens if we look at other ecosystems?
That's the real game changer. The sources show that if you integrate ERW into forests, where biomass is higher, soil dynamics are different, you could potentially triple the carbon sequestration.
Triple it. What are the peak projections in those scenarios?
In those really aggressive, ambitious scenarios, the scalability is projected up to 12 gigatons of CO2 per year. Now, we have to be cautious with that number.
Of course.
It represents a theoretical maximum, but it shows the sheer geological power of this mechanism.
And regionally, where does the potential lie? If you're a policymaker, where do you start?
You start where you have extensive cropland and accessible rock. The U.S. alone could sequester 0.16 to 0.30 gigatons of CO2 per year by 2050 in croplands.
Globally.
The hotspots are China, India, the United States, and Brazil. They have the land and the geology.
And the other critical factor is the climate itself. This is a chemical reaction, and chemistry speeds up when it's hot and wet.
Absolutely. Climate is destiny here. Research shows that the best conditions are in warm, humid regions, so the low latitudes between 40 degrees north and 30 degrees south.
So the tropics and subtropics.
Right. Those regions have weathering rates that are 3 to 5 times higher than in temperate zones like Northern Europe. If you want maximum bang for your buck, you focus there.
Oh.
Okay, so now let's transition to the major reality check. How do we take this gigaton potential and actually make it practical? We have to look at the big hurdles: energy, cost, and risk.
Let's start with the supply chain. We're talking about mining rocks, crushing them to a fine powder comminution, right?
Yep.
And then transporting that huge amount of material. This sounds incredibly energy intensive.
It is the Achilles heel of ERW right now. Mining, crushing, and transport account for a staggering 77 to 94% of the total energy needed. We are literally turning mountains into dust, and that takes a colossal amount of energy.
Can you quantify that in terms of the CO2 we're trying to remove?
The energy demand is very high, ranging from about 650 up to 3,500 kilowatt hours per net ton of CO2 drawn down. This translates directly into a carbon penalty.
So you're spending carbon to remove carbon.
You are. And the net efficiency, how much CO2 you actually remove after subtracting the emissions from the process, is entirely dependent on your energy source.
Right. If you're grinding rock with a coal-powered grid.
Your net removal efficiency could drop to 75% or even lower. To really make this work, you have to pair ERW with fully decarbonized energy systems. Clean energy is mandatory for this to work at scale.
And what does that mean for the cost?
Yeah.
What does a ton of removed CO2 cost a developer today?
It's highly variable, anywhere from $70 to almost $600 per ton. It just depends on local rock availability and energy costs.
It's a huge range.
It is, but the good news is that analysis projects those costs will decline. They're heading toward a much more competitive range of about 100 to 150 per ton by 2050.
Okay, moving from logistics to safety. When you accelerate a geological process by hundreds of thousands of years, what environmental risks are we introducing to our soils?
The primary risk is trace metal mobilization. Some silicate rocks, especially the ultra-basic ones like olivine, have naturally occurring heavy metals. Nickel and chromium are the big concerns.
And when you grind them up and speed up the weathering?
Those metals can dissolve into the soil water, which means they could pose, ecotoxicity risks to microbes or even contaminate crops. That's why careful feedstock screening is absolutely non-negotiable.
And finally, the monumental challenge of accounting.
Oh.
Monitoring, reporting, and verification, or MRV. Why is proving this works so much harder than, say, direct air capture?
It's the variability. Real-world weathering rates are uncertain. Often less than 10% of the rock might weather in a year. But the biggest challenge is what we call attribution complexity.
Attribution complexity, explain that.
Well, when that bicarbonate is formed in the soil, up to 20% of the CO2 that formed it might have come from soil respiration. That's CO2 released naturally by microbes or plant roots.
Ah, I see the dilemma. If I sequester carbon that a microbe was just about to breathe out anyway, I haven't actually removed it from the atmosphere.
Exactly. You've just intercepted a carbon molecule that was already cycling locally. To get climate credit, you have to prove you captured a CO2 molecule that recently came from the atmosphere.
Which sounds incredibly difficult.
It requires advanced and expensive MRV protocols. We're talking isotopic tracing, using markers like delta C13 to tell the difference. This is a major area of research right now.
We've hit the potential and the pitfalls. So let's wrap up by looking at the core decision points, the trade-offs that engineers have to constantly balance when they implement ERW. Let's start with the grinding trade-off.
This is a classic engineering problem. You want the fastest weathering, which means you need superfine particles, high surface area.
Right.
But grinding that finely is exponentially more energy intensive.
So it's faster CO2 capture versus a higher carbon penalty from the grinding. Where's the sweet spot?
You're forced to optimize. The energy you invest in grinding has to be justified by the net CO2 capture. And that sweet spot changes based on how clean and cheap your local electricity is. You might settle for coarser particles if your grid is dirty just to keep the net efficiency high.
Then there's the rock type trade-off. Speed versus safety. We've got basalt and olivine as the two main players.
And they are very different. Olivine weathers much faster. You can get up to 0.8 tons of CO2 per ton of rock. That speed is great.
But it has that higher risk of heavy metal contamination.
Exactly. Nickel and chromium. And then you have the slower option, basalt. It sequesters less, around 0.3 tons of CO2 per ton of rock, but it has a much safer trace metal profile. And crucially, it delivers more of those nutrients that boost the agricultural co-benefits.
So it's a deliberate balance between speed, safety, and farm profitability.
Right. And the final and maybe the most nuanced trade-off is the soil-carbon trade-off. It's often called the priming risk.
This sounds almost counterintuitive.
It is. The whole goal of ERW is to generate alkalinity to create those bicarbonate ions. But that high alkalinity, that increase in soil pH, can sometimes stimulate microbes to decompose the organic carbon that's already in the soil.
Wait, so the same change we're making to capture new carbon could cause us to lose the carbon that was already there?
Precisely. It's called priming. One incubation study, for example, showed a 13% net carbon loss because the alkalinity boost just sped up decomposition of the existing soil carbon. It means you have to manage this carefully to protect what's already there.
So synthesizing everything, what does the research say is the optimal deployment strategy for ERW right now?
The sources all point to three key things. First, use low-carbon energy for everything, mining, grinding, transport, to keep that net efficiency high. Second, apply moderate, repeated rates.
Not one big dose.
Right. Think 50 to 500 grams per square meter. High doses can lead to saturation and trigger that priming risk. And the third point relates to how new this research is.
We need to be adaptable.
Exactly. We need adaptive management. We still have huge knowledge gaps, especially on long-term, multi-decade field data. We have to treat this as a learning process as we scale. So, to summarize our deep dive, enhanced rock weathering stands right now at this critical juncture between massive promise and logistical practicality.
The promise is genuine. We're talking durable, gigaton-scale carbon removal that copies Earth's own blueprint for climate stability, and it delivers these powerful agricultural co-benefits: better yield, less N2O.
But it is not a simple solution. Its success hinges entirely on our ability to conquer those logistical and verification hurdles, primarily decoupling the supply chain from fossil fuels and developing cost-effective MRV that can actually distinguish atmospheric CO2 capture from the local carbon cycle.
It requires real systems thinking. You're connecting geology, chemistry, energy, agriculture. And that leads us to our final provocative thought for you, the learner. Given that almost all the long-term field trials monitoring ERW have been running for less than 5 years, yet the carbon stored is claimed to be durable for tens of thousands of years. What are the ethical and financial implications of investing heavily in a technology today when we won't fully understand its long-term ecological risks or cumulative sequestration rates for another 15 to 20 years?
Something to consider as you process this deep dive and assess the true viability of these geological scale climate solutions.
We'll see you next time.